was as good as we had in Ohio. It was really a nice weekend, almost like springtime. So today, um, we'll cover two topics, the basic refractory group, and then after that, a shorter section on insulating refractories, refractory brick and fiber materials. So the basic refractories there's 5 groups here: magnesite, dolomite, chromagnesite, forsterite, and spinel. And for each one of these materials, we're going to follow the same process that we did last week: raw materials, phase relationships, how these materials are processed, and then some of their key properties, and we'll examine the microstructure. So one of the raw materials for MgO refractories is magnesium carbonate. The mineral is known as brunerite. It's MgCO3. And there's 2 types of deposits, crystalline and cryptocrystalline. Crystalline deposits are fine to coarse crystals, and the cryptocrystalline deposits are very fine crystals. This one is 88% MgO, and the finer crystal size is 85% MgO. The impurities are SiO2, Al2O3, Fe2O3, and CaO, and they're there in several percent, depending on which one. So they're about 85 to 88% pure. Magnesium hydroxide, another mineral is brucite, that's MgOH 2 times. That's a scarce mineral, so it's not a viable raw material for MgO refractories, but it is a source of MgO. So heating up either one of these materials, the magnesium carbonate, brunerite, MgCO3, it decomposes at 650 degrees C. So MgCO3 yields MgO, and the gas that comes off is CO2. So that decomposes to MgO at 650 degrees C. Magnesium hydroxide mineral, brucite, MgOH2, decomposes at a lower temperature, about 300 degrees C. So the brucite yields MgO plus H2O gas. So those are 2 minerals that produce MgO and how they decompose. A large, maybe the primary source of MgO is from seawater. It turns out there's 0.013 weight percent magnesium in seawater. You can also get it from brine wells in the form of magnesium chloride. So it's a precipitation process. So in seawater, MgCl2 is in solution, even in the brine well. So MgCl2 plus the seawater H2O, you add lime to that, CaO, and that precipitates out a magnesium hydroxide. And now calcium chloride is in solution. So you take that magnesium hydroxide precipitate, and then you calcine it at a high temperature to make what's called a dead burn MgO. So calcine it at 1900 degrees C, and now you end up with MgO. MgO has a high melting point, 2800 degrees C, very refractory material. So that's the seawater process. So you have your precipitate MgOH2. If you heat it at 950 degrees C, you're going to have a calcined, low density porous MgO material. You can pelletize that. And I mentioned dead burning to produce a dense MgO, maybe 1600 to 2000 degrees C. So the higher the temperature, the denser it is, the lower the porosity, and it's a more hydration resistant material because MgO is subject to hydrate and go back to the brucite form, magnesium hydroxide. So the effect of dead burning temperature, or basically heating at a high temperature, this is specific gravity, this is crystal size, and this is hydration tendency, which in this case is just loss on ignition. So the higher the loss on ignition, the more hydration has taken place, or the higher the hydration tendency. So these three properties are plotted against temperature. So as you heat the MgO material, you increase the density, you remove the porosity, so it becomes denser. You have a higher specific gravity. The crystal size also tends to grow larger. So larger crystal size with increasing temperature. And then this factor hydration tendency goes down as you decrease the porosity and make a dense structure, lower surface area. So at a higher temperature, you have a lower loss on ignition when you run a hydration test. So that's a lower number, and it's more resistant to hydration. So that drops off rather quickly at about 1600, 1650 degrees C. So you have to make it dense to prevent it from rehydrating and forming the magnesium hydroxide. It's not a fast process, it's relatively slow. It's not the same as when lime rehydrates, which is a fast process. It's a much slower process, but it still can hydrate. So the magnesium oxide that comes from seawater is a relatively high purity. There's a regular grade and a high purity grade. So the regular grade is 95 to 98% MgO, and the high purity is 99.5 to 99.8. So it's very high purity. SiO2, Al2O3, Fe2O3, and CaO are the impurities, and they're just the balance. So in the high purity material, these concentrations are quite low. So both grades of seawater MgO are quite pure. And if we look at the phase relationships, two of the impurities are CaO and SiO2. So obviously magnesium is present in great excess, 98, 99% in a good MgO material. But you do have calcium and magnesium silicates, and they are fixed by the ratio of CaO to SiO2. In order to keep an MgO as a high temperature refractory, you have to maintain a high ratio of CaO to SiO2, because if it's a low ratio, you have low melting eutectics. So you need a higher lime concentration than an SiO2 concentration in the impurities to eliminate low melting eutectics. So these impurities, CaO and SiO2 and the other impurities, they're concentrated at the grain boundaries between the MgO crystals, and they're in the bonding matrix between the MgO crystals. So they're there in low quantities, but they're concentrated, and they can form some low melting materials. So CaO to SiO2 ratio less than 1.86, and this is weight percent ratios. You can develop liquid phases at 1575 degrees C. If you have this combination present, magnesia, a dicalcium silicate, and a phase known as merwenite. So that's the eutectic, 1575. That is below steelmaking temperatures, and MgO is a material used to line basic oxygen furnaces where you make steel. So that's undesirable. Or if you have the combination magnesia, merwenite, and monazite, Murronite and monocellite are low melting materials, and the eutectic is even going to be lower, 1490 degrees C. But if you have the lime to silica ratio greater than 1.86, the first liquid phases that develop are at 1790 degrees C, which is the eutectic between magnesia, dicalcium, and tricalcium silicates. So this is above steelmaking temperature. So that's why you want to have this ratio higher than 1.86. So this is the silica lime MgO ternary phase diagram. The primary phase field for MgO or periclase is right here. And if you go around this in like basically a clockwise direction, you'll see the phase fields that are in contact with MgO. There's lime, there's tricalcium silicate, there's dicalcium silicate, there's murronite, which is 3CaO MgO2SiO2, so it's a calcium magnesium silicate. There's monocellite, which is CaO MgO-SiO2, another calcium magnesium silicate, and then phosphorite, which is the MgO 2-MgO-SiO2 material. You can see the eutectics here, 1502, 1575, and the melting points are in here also. Looks like 1485 and 1450. So you have a high temperature material in contact with some low melting materials in this region here. And to make a simplified version of this diagram, here's CaO, SiO2, and MgO. And we're just drawing the tie lines between MgO and the different compounds that we just mentioned. So this is MgO tricalcium silicate, MgO dicalcium silicate, MgO murronite, MgO monocellite, and MgO phosphorite. So the chemical compositions are right here. And then right here is the ratio 1.865 to 1 along this tie line. So ratios lower than this, you're going to end up with the murronite and monocellite in the grain boundary areas or in the matrix. So you need to have a lime to silica ratio greater than this number so that the phases are going to be present are MgO, CaO, tri and dicalcium silicates. So this is a table that just summarizes that. So parts per weight of CaO to SiO2, here's 1.86. What you expect to see is dicalcium silicate. And if you're higher than 1.86 to 2.8, dicalcium and tricalcium silicates, higher than 2.8, tricalcium silicate, and even higher than that is tricalcium silicate and lime. So these are all high temperature materials right here. When you go in the other direction, 1.4 to 1.86, you have dicalcium silicate, which is a high temperature material, but now you have murronite, which is a lower melting material. When you're down to 1.4, you're just going to have murronite. 0.93 to 1.4, you have this combination monocellite and murronite, both low melting materials with low melting eutectics. And 0.93 is just monocellite. And when you get all the way over to less than 0.93, you now have phosphorite plus monocellite. Phosphorite's a high temperature material, but it's also, you also have a monocellite present as the equilibrium phases. So when you have an MgO raw material, you want to make sure you have a lime to silica ratio greater than 1.86. That's always important if you're going to be using at high temperatures. Some of the applications for MgO refractories, if there's a low temperature application, you may not have to worry about that. You can have perhaps a higher silica to lime ratio than 1. So these are the compounds we just talked about, and these are their melting points of the different eutectics. And the last column is degree C, the first column is degrees F. So the eutectic between MgO and CaO, we showed this when we talked about corrosion in phase diagrams. It's 2300 degrees C, MgO, CaO, and the tricalcium silicate is 1850 C. MgO, tricalcium, and dicalcium silicates were still high temperature materials. The eutectic is down to 1790. MgO and dicalcium silicate is still high, 1800. But now, when you have MgO, dicalcium silicate, and murronite, it's down to 1575. And then the combination of MgO, murronite, and monocellite is now down to 1490. And then MgO, monocellite, and phosphorite is still low, 1502. And then when you have MgO and dicalcium, and MgO and phosphorite, it's back up to 1860. So you need to avoid these calcium, magnesium silicate materials, murronite and monocellite. These are the melting points of the different materials we just talked about. Lime is 2570 degrees C, and MgO is 2800 degrees C, both very refractory materials. The MgO can also form a spinel with the alumina Al2O3 impurity, and that's a high melting material, 2135. We'll discuss that later this morning. Dicalcium silicate is 2130 degrees. And phosphorite, which is another basic refractory we'll discuss later this morning, 2-MgO SiO2 is 1900 C. So those are all high temperature materials. The tricalcium silicate is stable at high temperatures, but tends to dissociate into dicalcium silicate and lime at temperatures below 1250 degrees C. You also have Fe2O3 present, and that can form a dicalcium ferrite, which melts at 1436 C. You can form magnesiopherrite. The Fe2O3 can combine with MgO. That's still a pretty high temperature material, 1713 degrees C. And then we mentioned monocellite and murronite, 2709, well, 1487 degrees C and 1577 degrees C are where they melt. So those are all the possible compounds with the impurities that you find in MgO and their melting temperatures. This slide was the phases and their eutectic melting temperatures. So if we look at some more phase diagrams, FeO, MgO, and Fe2O3, MgO. So one good thing about MgO, it can tolerate large amounts of iron oxides in either one of these forms. So in a steelmaking application, if FeO or Fe2O3 penetrates the MgO grains or crystals, you still have high temperature material. So ferrous oxide, FeO, forms a complete solid solution with MgO, and that's known as magnesiowustite, FeO, MgO. SS means solid solution. So there's a very gradual decrease in the temperature of liquid formation as the FeO content increases. The ferric oxide form of iron, Fe2O3, forms a magnesiopherrite, MgO, Fe2O3, which melts at, we just said a few minutes ago, 1713 degrees C. So this is the MgO FeO diagram. This is 100% FeO going to 100% MgO in that direction. This is in temperatures in degrees Fahrenheit. So MgO is 5070 degrees F for its melting point, and FeO melts at 2500 degrees F. So below this bottom dotted line, everything is solid. It's all magnesiowustite. Above the top dotted line, everything is liquid. In between, you have a combination of magnesiowustite and liquid. But as you see here, even adding 10% FeO, you're still at a very high temperature. So you can tolerate quite a bit of FeO substitution into MgO and still have a high temperature material. The other one is MgO Fe2O3, and this is temperature in degrees C. This is 100% MgO, and then this is 100% Fe2O3. But even if you're adding, let's say, 10% Fe2O3, you're still in this magnesiowustite phase field. So this is solid magnesiowustite below this line and in this phase field. And then over here, we have magnesiowustite in liquid and then all liquid. So you can tolerate quite a bit of addition of Fe2O3 and still have a high temperature material. 20% of Fe2O3, you're still at 2400 degrees C. So MgO can tolerate iron oxide in its different oxidation states. And that's desirable in steel making applications because obviously steel is Fe. B2O3 is an impurity, trace impurity that's in seawater. So we need to look at the B2O3 MgO phase diagram. MgO cannot tolerate even small amounts of boron oxide. It's a very powerful fluxing agent. It really lowers the melting temperature. So boron oxide forms a liquid with MgO at 1333 degrees C, quite a low temperature. So if you have boron oxide, B2O3, present in, this is really trace amounts, 0.02%. Anything greater than that, you're going to start affecting its hot properties like hot strength. So when you buy a seawater MgO, you have to make sure the boron content is quite low. So this is the MgO B2O3 phase diagram. This is 100% B2O3 and then 100% MgO. And this is in degrees centigrade. So at 100% MgO, if you just add a trace amount of B2O3 and you go up in temperature and you see here 1333 degrees C, you have MgO in liquid. So M is MgO in liquid. So any small amount of B2O3, you're going to start forming liquid. Obviously, the more B2O3, the more liquid you're going to form, but trace amounts form enough liquid in the grain boundaries to make the mechanical properties at temperature inferior. B2O3 and SiO2, both impurities. Silicon cannot tolerate small amounts of boron oxide, just as MgO cannot tolerate small amounts. So boron oxide forms a liquid with SiO2 at less than 1200 degrees C. So if these phases, again, are concentrated in the grain boundary, your hot strength will be inferior because boron oxide can also form react with the silica as well as with the MgO. So this is the phase diagram for SiO2 and B2O3, 100% B2O3 and 100% SiO2, and then temperature in degrees C. So you have quartz and B2O3 at a low temperature, and we're going up at a low concentration of B2O3. You have quartz in liquid, liquid starting to form above 400 degrees C. Then you have tridymite in liquid above 800 degrees C. And then finally, you end up with cristobalite in liquid. But in all cases, you're forming a liquid at a very low temperature. So it's important to have an MgO material with a low boron content. So to make an MgO refractory, you start out with this dead burned MgO, which is the material that's been calcined at a high temperature to densify it. It's crushed and screened into the appropriate proportions according to particle packing to give you a maximum density. It goes through a mixing step where water is added. You can also add Fe2O3 as a sintering aid. We just mentioned that MgO can tolerate large amounts of Fe2O3, so it can be used as a sintering aid to promote the sintering and densification process. These materials are pressed and dried and then fired 1600 degrees C to 1800 degrees C. Conventional MgO is MgO that has a silicate phase present, and that's usually fired at a low temperature, 1600 degrees C. A direct bonded would have lower impurity content and be fired at a high temperature, 1800 degrees C. So direct bonded has MgO crystals in contact with each other in isolated regions of low melting phases, low melting silicate phases, and a conventional MgO refractory has the low melting silicate phases present at the grain boundaries and in the matrix. So microstructure and properties. If it's a conventional bonded MgO, you have coarse and fine grain MgO particles separated by a silicate phase. So the silicate phase is now what's going to control the high temperature strength and creep behavior. If it's direct bonded, you have coarse and fine MgO grains in direct contact. You have a lower amount of impurities, so a low amount of isolated high melting silicate phases. And now the bonding between the crystals, the direct bonding controls the high temperature behavior. So direct bonded materials are higher purity materials, and then they're fired at high temperatures to promote crystal to crystal bonding. And this is a microstructure of an MgO refractory. The lighter phase are the MgO crystals. You can see that a lot of crystal contact at the grain boundary, so there's quite a bit of direct bonding here. This darker gray region is the silicate matrix. It's a combination in this material of phosphorite and monticelite. So that's what an MgO microstructure looks like for a material that really is exhibiting more direct bonding and a lower amount of the silicate phase. Here's a sample that we've looked at it in our lab. This is 35x magnification. This is an MgO that has about 92% MgO, almost 2% lime, and a little more than 4% silica, and an iron and an alkali impurity. Notice that the lime to silica ratio is not greater than 1.86. So this is a material that'll form a low melting eutectics rather easily. The dark black phases are the porosity. You can see the outline of MgO crystals or grains with crystals, and then the matrix is in between the larger grains. So if you go up to 200x, here's a large MgO grain, 100% MgO basically. The black again is the porosity. And then you can see that there are two phases between the MgO crystals, a darker gray and a lighter gray. And if you look at the MgO crystals, the darkest gray phase you can see that there now no longer a lot of crystal to crystal contact. There's a lot of silicate phase between the MgO grains or crystals. And you would expect that because it's a fairly high impurity level, almost 9%, and the silica to lime ratio is in the wrong direction. So this darker gray secondary phase is about 55% MgO, 3% CaO, and 41% SiO2. So that is probably a phosphorite, a higher temperature grain boundary phase or matrix phase. And then this one, the lightest gray phase, is about 29% MgO, 34% CaO, and about 37% SiO2. So that ratio of these materials, about each being about 1/3, this is probably monticelite. So it's a low melting silicate phase. So this microstructure is quite a bit different than this one. This one is primarily direct bonded. This one has a silicate phase separating the MgO crystals. So the deformation under load, which is basically your hot strength and your creep resistance. Upper temperature limit is determined by the amount and melting behavior of the silicate phases. The corrosion resistance is excellent in basic environments. It's a basic refractory, and it can tolerate large amounts of iron oxides. So in the steel making process, which is a basic oxygen furnace, they're running a basic slag, and you have iron present. So that's why it's used there, because has excellent corrosion resistance. Its thermal shock resistance is poor. We mentioned last week that it has the highest thermal expansion of all the oxides that you can make a refractory with. So it's going to have poor thermal shock resistance, excellent corrosion resistance, and mechanical behavior at high temperature depends on its impurity level. So again, most refractories are like this. Some of it, you have an excellent property here, but you have to balance it against a property here that's poor. These are some MgO refractories. All of these tables that I show are taken from data sheets. A 91% MgO, a 98, and another 98% MgO. The densities are in the 180 plus pounds per cubic foot. Typical porosities all around 15, 16, 17%. Fairly good cold MOR, very good cold crushing strength or compressive strength. The hot MOR is relatively decent for the two 98% MgOs, 1100 and 1600. That's in PSI at 27 and 2800 degrees F. This one is not reported or not available. And if you look at the MgO levels, they should correspond to what their advertised are at 91%. And then these two are close to 98%. The first one has a lime to silica ratio about 1/2, which is much less than 1.86. But these other two have a high lime to silica ratio, both of these. So this one has low melting compounds and eutectics in it. It has a high impurity level, 9%. So they don't even bother to measure the hot strength because we know it's going to be relatively poor, but it's still a useful material. It's probably used in an application that's at a much lower temperature. Fe2O3 and Al2O3 are the other impurities that are present. So that was MgO. Are there any questions on that refractory material? So MgO is a relatively more expensive refractory material. Dolomite is a relatively cheap material. present in mineral deposits, and there's quite a bit of it in this country. So it's a relatively cheap raw material. So dolomite is just a combination of MgO and CaO. And in the mineral, it's a solid solution of MgO and CaO carbonates. So solid solution of MgCO3 and CaCO3. There's usually a little bit more Ca than Mg, but the ratio is closer to 1. This has a eutectic at 2370 degrees C. So it's a high temperature material, and it's relatively inexpensive, but as we mentioned on the first day, it has a hydration issue. So here are two minerals as mined, one in this country and one in China. The loss on ignition when you drive off the CO2, when you decompose the carbonates, is almost half of the weight. So this is 47 and 40, almost 47 again, weight percent comes off as CO2. Then you end up with about 31 or 32% CaO and about 20% MgO, and silica, alumina, and your iron oxides are your typical impurities. So you start out with dolomite, the carbonate version, you apply heat. The magnesium carbonate decomposes first, 775 degrees C. So when this dolomite decomposes, you now have MgO plus your calcium carbonate plus CO gas that comes off. And then you take it to a higher temperature, 1870 degrees C, and then the calcium carbonate decomposes. So now MgO plus calcium carbonate equals MgO plus CaO plus CO2. The MgO crystals are dispersed in a continuous matrix of the lime crystals, CaO crystals. The density of CaO is lower than that of MgO. So even if it's a 1-to-1 ratio of MgO to CaO, the CaO is going to be the continuous matrix with the MgO crystals dispersed in it. And since CaO has very poor resistance to hydration, it's thus the way the material is, it's the portion in the matrix that's exposed to the water. And the MgO is in isolated crystals. So MgO can hydrate, but it's a really slow hydration rate compared to the hydration rate of CaO. So you have a magnesium, calcium carbonate solid solution. You can pre-calcine it at 950 degrees C and end up with MgO, CaO, very porous material. You can form that into pellets and then dead burn it at 1600 to 2000 degrees C, or you can just take the dolomite material and dead burn it directly, and you end up with a dense MgO CaO material, with CaO being the matrix, with the MgO crystals dispersed in the matrix. This is bulk density and porosity versus firing temperature. So what happens during dead burning? You start out at room temperature, and in the temperature range, 700 to 900 or so degrees C, where the carbonates decompose, the density goes down. It stays fairly constant until you reach a high enough temperature again, maybe 1300 degrees C, where the material starts to sinter and densify, so the density increases. So this is where it's dead burned over here. And if we look at the porosity versus temperature, this is the porosity, maybe 10% in the dolomite. But then as you decompose the carbonates, the porosity goes up to about 50%. So it's very porous at this point. And then as you densify it at higher temperatures, the porosity goes down. So these are just two different materials, an A and a B, two different dolomites. So this is the phases that are present versus temperature. So you start out with 100% dolomite. And the first thing that decomposes is the magnesium carbonate. So it starts to decompose at about 600 C. And this solid line represents the increase in MgO content as the magnesium carbonate decomposes. The calcium carbonate is still stable to maybe 800 degrees C or so. So that concentration is increasing. And then when it starts to decompose, the calcium carbonate concentration decreases, and then the lime concentration increases as the carbonate concentration decreases. So you end up with a mixture of MgO and CaO, about a 1-to-1 ratio. So there's two issues associated with processing and using dolomite refractories. And we mentioned hydration resistance. It's extremely poor. CaO reacts with water and disintegrates. So CaO plus H2O yields the calcium hydroxide. So if you made a, let's say a refractory out of dolomite, and in the summertime, especially in Ohio where it's humid, if you let that brick sit out, 2 weeks later you come back and look at it, it's going to be completely hydrated and disintegrated into a pile of powder. So it has very poor hydration resistance. The dicalcium silicate, 2CaO SiO2. If you have silica present, and you have silica present in a lot of slags that are in contact with dolomite refractories, there's a beta to gamma crystalline structure transformation. And that takes place upon cooling at 725 degrees C. And when that transformation takes place, there's a 10% volume increase. So dolomite is commonly used in AOD vessels, argon oxygen decarbonization vessels for making stainless steel. And there's a silicate slag. So that slag tends to diffuse into the hot face of the dolomite refractory, forms dicalcium silicate. And if you cycle that furnace, the sample will tend to disintegrate as it's cooled down below this temperature. So two issues with dolomite. The first one is a serious issue, the hydration resistance, and this formation of dicalcium silicate if you have it in contact with a silicate slag. MgO melts at 2800 degrees C, CaO melts at 2570 degrees C, and we mentioned the eutectic is 2370 degrees C. Very high melting points. We showed the phase diagram last week for CaO and MgO. There's limited solid solution between these end members. So this is the phase diagram that we showed, 100% MgO and 100% CaO with temperature in degrees C. And these regions on each side of the phase diagram are the solid solution regions. So again, MgO is over here. You can dissolve a small amount of CaO into MgO to form a solid solution. And then CaO is over here. You can dissolve a small amount of MgO into CaO to form a solid solution. So it's not exactly pure CaO or pure MgO. There's some of each component dissolved in it. And then this is the two-phase region of MgO solid solution and CaO solid solution. The first liquid forms at 2370 degrees C. And then this is the eutectic, the lowest melting material. So again, this is MgO plus liquid. This is CaO plus liquid. And then above this curve, the liquid is curved, it's all liquid. So dolomite is a high temperature refractory material. It's mined, it's plentiful, and it's relatively cheap compared to other basic refractories. Unfortunately, it hydrates when in contact with water. Al2O3 and Fe2O3 are impurities in dolomite. They form these different compounds. This one is 4-CaO, Al2O3, Fe2O3. That's brown millerite. It melts at 1450, 15 degrees C. So it's a relatively low temperature material. And dicalcium ferrite, 2-CaO, Fe2O3, melts at 1436 degrees C. So when you process dolomite, you take your dead burn material, MgO-CaO, and again, it's a dry pressing operation, so the material is crushed and screened to produce a particle size distribution for maximum density. You can add Fe2O3 as a sintering aid. You have to be careful how much you add. If you have these types of reactions taking place, you're going to form some low melting materials. Now, when you go to dry press this, you can't use water, so you have to use some kind of organic liquid. Otherwise, you rehydrate the CaO portion of dolomite. This material is dried, fired up to 1700 degrees C. And then immediately after firing, it has to have go into moisture protection. So there may be a coating applied to the refractory, an organic coating to prevent it from hydrating. It's definitely going to be shrink wrapped in plastic and then goes into cold storage, air conditioned storage with low humidity. So these refractories have a shelf life of approximately 3 to 6 months in storage. The trick is getting them out of storage to, let's say, a steel plant where they're making stainless steel, getting them in the furnace very quickly and up to temperature. So as soon as they're up to temperature, they're not going to hydrate anymore. But the trick is to get them shipped to a site where they're going to be installed, get them installed as quickly as possible and up to temperature. And once you do that, you have an excellent refractory. The microstructure and properties sintered material is MgO crystals dispersed in a polycrystalline CaO matrix. So the matrix is the bonding phase. Basically, it's not protected from hydration, so the CaO is exposed, whereas the MgO crystals are not. A typical dolomite refractory is about 58% weight CaO and about 42% weight MgO. It has relatively good thermal shock resistance. When you add CaO to MgO, it lowers the thermal expansion compared to pure MgO. So dolomite has a little bit better thermal shock resistance than pure MgO, and it has good corrosion resistance, again, in a basic environment. So a basic slag high in lime would be compatible with the basic refractory. Some applications for dolomite. I mentioned an AOD vessel, but they're used in rotary cement kilns and refining furnaces. The bulk density is over 180 pounds per cubic foot. The porosities are typical, 10 to 20% range for you see for most refractories. Relatively high cold crushing strength, fairly good hot bending strength or hot MOR, 1000 at 2550 degrees F. And these are the MgO and CaO levels. A range is given for each one of these materials. So that's the dolomite section. If there are any questions, let me know. Otherwise, we'll go to the next section, chrome magnesite. So we started out with MgO, we added CaO to form dolomite. Now we're going to add chrome to the MgO for the chrome magnesite refractories. The mineral is chromite. It's a spinel, FeO, Cr2O3. The spinel is just a crystal structure. Spinel is RO, R2O3. So RO could be FeO or MgO. So those are the RO groups. R2O3 can be Cr2O3, Al2O3, or Fe2O3. So that's the R2O3 group. So spinel is 1 to 1, one RO to one R2O3 group. So chromite has all of these present. It has Cr2O3, Al2O3, Fe2O3. Each one of these R2O3 groups can combine with an RO group. So for example, Cr2O3 can combine with FeO to form that spinel, FeO Cr2O3. It can combine with MgO to form that spinel, MgO Cr2O3. And likewise, Al2O3 can form two spinels, and Fe2O3 can form two spinels. So there's 6 different chemical compositions that can form in this chromite mineral. And these are the relative percentages present in the R2O3 groups. It's about 40% Cr2O3, 55% Al2O3, and Fe2O3 is a low amount. It also contains about 25% FeO and 75% MgO in the RO groups. So that's the breakdown in what's present. You can see that in the Cr2O3 level in a chromite mineral is not that high because of all these other oxides that are present. Unfortunately, in chromite, the ore has a lot of other minerals. Serpentine, which is a hydrated magnesium silicate, 3MgO, 2SiO2, 2H2O. Clinochlor, which is a magnesium aluminosilicate that's hydrated, so it can be 5MgFeOs, Al2O3, 3SiO2, 4H2O. So this varies, but the sum of these two is 5, whether it's MgO or Fe. Feldspar, which is a calcium aluminosilicate, CaO, Al2O3, 2SiO2, plus other low melting silicates. So besides having alumina, Fe2O3, FeO, and MgO forming all these spinels, you have other minerals present, and that gives a low melting point. So it doesn't even have a melting point because you have so many silicates present. You have a glassy phase, so it exhibits a melting range. It's basically, the matrix is a silicate, which is a glass. Glass does not have a distinct melting temperature. It just softens as you increase the temperature. So the chrome ore doesn't have a distinct melting point. It just becomes less viscous as you increase the temperature. And that's a function of the spinel phases and the silicate phases that are present. Some of these silicate phases are melting at low temperatures as low as 1260 degrees C. So the chrome magnesite materials are rather messy with all the different possible chemistries and compounds and silicate phases that can form. Here are 3 chrome ores, one from South Africa, one from Japan, and one from the Philippines. The chrome content, Cr2O3, is about 48% here, 30% here, and 33% here. You can see there's quite a bit of MgO, 11, about 21, and about 17%. The FeO is high, about 17, 8, and 11. Fe2O3 about 9, 4, and 3. Quite a bit of Al2O3 present, around 10%, 24 and 28. And then some SiO2, about 3.5, 8, and 4, and a small amount of lime. So that's what the chemistry looks like for the chromors. So when you apply heat and you increase the temperature, and if it's an oxidizing atmosphere, if there's excess oxygen, Fe2O3 is the stable form. FeO will oxidize with excess oxygen and go to Fe2O3. So the Fe2O3 in the spinel phase is unaffected, but the FeO in the spinel phase is oxidized to Fe2O3. So that decreases the RO content and increases the R2O3 content in these spinels. It becomes unbalanced, and then two phases appear. So you have more R2O3 than RO, so the spinel is unbalanced. So the MgR2O3 spinel, and again, R2O3 can be any of these three, Fe2O3, Cr2O3, and Al2O3. And then you have a solid solution of excess R2O3, and they can be the same three compounds based on Fe, Cr, and Al. So now you have excess R2O3. It forms needle-like inclusions in the chrome grains. So it precipitates in the chrome grain, basically has a volume expansion, so it can disintegrate the chrome grains. And here's an example of a chrome grain at high magnification. The white needles are this precipitate, CrFe2O3 precipitate. And if this occurs in a large amount, there's a volume increase and it can disrupt the structure. If you heat it in an atmosphere that's reducing, a low amount of oxygen present, the FeO in the spinel is unaffected. It's stable in a reducing atmosphere, but now the Fe2O3 is readily reduced to FeO. So the Fe2O3 in the spinel is reduced to FeO. So if your chromor contains Fe2O3, or if you have a chromor that's been heated in an oxidizing atmosphere, it will definitely have Fe2O3. You will reduce the Fe2O3 to FeO, and that's another volume expansion, and that could cause cracking. So what happens when you repeatedly oxidize and reduce this material, it keeps cracking, and it eventually causes extensive cracking and disintegrates the material. So how do you make chromor a more useful material? Well, you have to add MgO to it. The MgO does several things. It reacts with the silicates and forms phosphorite. We mentioned that phosphorite to MgO SiO2 is a higher temperature material, melts at 1900 degrees C. So you add MgO to tie up the silicates, remove the low melting silicates, make a higher temperature matrix. And then the MgO balances the RO, R2O3 spinels as the FeO is oxidized to Fe2O3. So MgO now enters the spinel to replace FeO, combines with any FeO that's oxidized to Fe2O3, and maintains the spinel structure MgO Fe2O3. So you tie up the silicates, you balance the spinels. A little bit more here. The MgO stabilizes the spinel structure in oxidizing atmospheres. It increases the melting range because that spinel that forms with the MgO has a higher melting point than spinels that form with the FeO. So MgO and any of the R2O3 groups in spinel is going to have a higher temperature than FeO in one of these R2O3 groups in that spinel form. So to increase the use potential of chrome ore, you add MgO. So these are the different spinel minerals and their melting points. FeCr2O3 usually decomposes before melting because it oxidizes. MgO-Cr2O3, 2180 degrees C, it's a high temperature material. FeOAl2O3, still high temperature, 1780. MgOAl2O3 is 2135. So you can see that an MgO-based spinel is going to have a higher melting temperature than an FeO-based one. And then FeO, Fe2O3 is low melting material, 1594. And then the MgO Fe2O3 spinel is going to be higher at 1713. So that's the melting points of the 6 possible spinels in a chrome ore. So when you process a chrome magnesite combination, if there's more chrome than MgO, if chrome is the major component, greater than 50%, it's called a chrome magnesite refractory. If magnesite is higher, if it's the major component, greater than 50%, it's magnesite chrome refractory. So you're taking chrome ore and a dead burned MgO, and you're going through the same process for dry pressing. The ore or the dead burned MgO is crushed and screened into the appropriate sizes and mixed for optimum particle packing. You can add water here with the powder to form a dry pressing operation. The sample is dried. There's probably, in all of these, there's probably a small percentage of an organic binder mixed with the water to give it some green strength after dry pressing. And then after drying, it's fired. If it's fired at a low temperature, 1400 degrees C, it'll be a conventional material, chrome magnesite or magnesite chrome material, and direct bonded, fired at a high temperature, 1800 degrees C. So it'll be direct bonded chrome magnesite or magnesite chrome. So if we look at conventional bonding versus direct bonding, conventional bonding, it's sintered at the lower temperature. Direct bonding is sintered at the high temperature. So in a lower temperature material, you have coarse and fine chrome and MgO grains separated by phosphorite, 2MgO-SiO2. That's the higher melting phase. You can have monticelite present. The silicates can combine with CaO and MgO. And you can have low melting silicate phases. So monticelite is a low melting phase, and the glassy phases, the silicate phases, are also going to deform at low temperatures. They don't have a distinct melting temperature, but the viscosity of these phases are going to decrease substantially as you increase the temperature. If it's direct bonding, fired at higher temperatures with material that has less impurities, now you're going to have coarse and fine chrome and MgO grains in contact with each other. You're going to have isolated regions of this other phase, phosphorite, the magnesium silicate, and high melting silicate phases. So now the crystal-to-crystal contact is going to control the high temperature behavior. So the deformation behavior is going to be excellent. The hot strength is going to be excellent compared to a conventional material. Here's a microstructure of either a chrome magnesite or magnesite chrome material. This large white crystal is a chrome grain. These smaller, slightly gray crystals that are rounded are the MgO crystals. This one it's from the literature. It's not especially well polished, but in between all these angular particles, which are the crushed chrome grains, and the MgO crystals is a matrix. You can see some of the fines, and that's where your silicate matrix is. Here's a higher magnification. So here's a chrome grain. And these are also chrome grains smaller. These are your MgO grains. They have a precipitate. There's some iron present, so there's a MgO Fe2O3 precipitate. And then these gray areas are your silicate matrix. This is porosity, these dark gray areas. So chrome grains, MgO grains with an iron precipitate, iron causing the MgO Fe2O3 precipitate, and a silicate matrix, silicate in the matrix. So here's an example of something we looked at in our lab at 25X. The composition is about 45% MgO, 27% Cr2O3, 14% Fe2O3, 12.2% Al2O3, low lime content 0.6, and some silica present about 1%. So this is a typical magnesite chrome refractory. We'll call it magnesite chrome because the MgO content is higher than the Cr2O3 content. In this material, the dark black is still the porosity. These angular shaped grains are the chrome grains. This one is about 51% Cr2O3, 18, 19% Fe2O3, 16% MgO, 13% Al2O3, and some silica present. These darker gray grains are the MgO. This happens to be a 90% MgO that was added to the chrome ore. The balance is Fe2O3, Al2O3, SiO2, and CaO. So it's primarily MgO and Fe2O3 over here. So you can see coarse grains. Here's another MgO grain. All these brighter grains are chrome. You can see an MgO with an iron precipitate, and there's a matrix phase. So if we look at 200X, we can see this matrix phase a little bit better. This is a chrome grain. Here's your MgO grains, and you can see the individual MgO crystals and their grain boundaries. This has excess Fe2O3, so there's an Mg-Fe2O3 precipitate in the MgO crystals. These gray, medium gray areas are your silicate phases. So there's some direct bonding and there's some silicate phases present. So if you map this, red here is for Cr, chromium. You can see the distinct large chrome grains and some of the smaller ones. If you map the MgO in orange, you can see the MgO grains. The little dark spots in there are where there's a higher iron concentration in the precipitate. You can see where the chrome grains were because there's no MgO in them. The Al, aluminum, is concentrated in the chrome grains. So wherever there's a chrome grain, there's aluminum present. Iron is everywhere. There's some in the chrome grains, and we saw the precipitates where the iron is more concentrated in the MgO grains. So it shows up as the precipitates in the MgO grains, and it's also present in the chrome grains. The green is silicon. So this is the silicate matrix. You can see it shows up between all the different MgO grains and MgO and chrome grains. So this would be your low melting material. And it is not continuous, it's fairly isolated. So there's a fairly large degree of direct bonding and some silicate phase also present. So for properties, deformation under load, the upper temperature limit is determined by the amount and melting behavior of the silicate phases. So if it's direct bonded, a pure material, direct crystal contact, it's going to have good high temperature strength and creep resistance. And the thermal shock resistance is fairly good. It's got a lower thermal expansion coefficient than pure MgO because the chrome lowers the expansion. So it has reasonably decent thermal shock resistance. Here's a couple examples of manufactured products, a 50, a 60, and 80% MgO. And now these densities are close to 200 pounds per cubic foot. Typical porosities for manufactured, pressed, and fired refractory about 16, 17%. The cold MOR is not that high. The hot MOR is much lower than a lot of other materials. This one is 160 at 2700F. This is 500 at 2700F. And the MgO content ought to correspond to the grade that it is, 50, 60, and 80% MgO. And you can see the balance is the chrome level, the Fe2O3, the Al2O3, SiO2, and a small amount of CaO. So as you go up in MgO content, the chrome content is obviously going down because you're adding more MgO. These other impurities are going down that are in the chromeware also because you're simply adding more MgO. So the next group of basic refractories we mentioned, phosphorite as a secondary phase in MgO and the chrome magnesite materials or the magnesite chrome materials. So by itself, it is a refractory material. So again, phosphorite is the 2-MgO-SiO2 magnesium silicate material. And by itself, it's a refractory. 1890 degrees C is its melting point. It's 57.3% MgO and 42.7% SiO2. The raw material is olivine. Olivine is a solid solution of this desirable phase phosphorite and an undesirable phase phthalate, or undesirable mineral. So phosphorite is F2Fe2, 2FeO, sorry, phthalate is 2FeO SiO2. It melts at a low temperature, 1205 degrees C, whereas phosphorite is 1890 degrees C. So in the olivine raw material, about 15% is actually phthalate. So that's quite a bit. So it can develop large amounts of liquid at a low temperature. Also, olivine can contain other minerals, serpentine and talc. So these are two hydrated magnesium silicates. This one is 3-MgO, 2-SiO2, and 2H2O. This one is 3-MgO, 4-SiO2, 2H2O. So if we look at the phase diagram for olivine, it's a solid solution of phosphorite and phthalate. So this is phosphorite, this is phthalate. You can see phosphorite has the high temperature for melting, 1890, and then phthalate is 1205 degrees C. So again, on the solid solution type phase diagram, everything below this line, the solidus curve is solid. Everything above the liquidus curve is liquid, and in between, you have olivine plus liquid. So you can see how the presence of phthalate really lowers the melting temperature of phosphorite, and 15% is probably about right here. So you're going almost 200 degrees drop in the raw material because of the 15% phthalate. So here are three raw materials, a Russian, one from Norway, and one from North Carolina. They all have about 40–41% SiO2, about 47–48% MgO. And then here's your contribution from phthalate. The Fe2O3 level is about 11, 8, and 7. And there's also some alumina present. Also, the other minerals that can be present, serpentine is about 60.5% phosphorite and 39.5% liquid at this temperature, 1559 degrees C. And talc at this temperature, 1544 degrees C, is 4% cristobalite and almost 96% liquid. So these are low melting materials that are in olivine. And if you look at the MgO SiO2 phase diagram, this is 100% SiO2, this is 100% MgO, and this is temperature. If you're to the left of phosphorite to MgO SiO2, if you're in this region here, you have two phases, MgO and phosphorite, and no liquid forming till 1850 degrees C. But if you're on the other side of this phase diagram, higher in the silica content, you have these low melting materials, liquid forms here at 1557 and then 1543. So this is where serpentine is, and this is where talc is. And I mentioned serpentine melts or forms liquid at 1557 and talc at 1543. So high silica content above the stoichiometric amount for 2-MgO SiO2, you're going to have issues with low melting materials. Also, there's another phase diagram we should look at, MgO SiO2 FeO. And in that ternary phase diagram, there's a region where you have low melting compounds as low as 1450 degrees C. So this is MgO, FeO, and SiO2. And depending on the ratio of FeO to SiO2, you can be in this region here where you have some low melting materials. You can see the temperature is 1305, 1470, 1177. So if you're in this region, you can also have some low melting materials. So how do you improve olivine? And just like for the chrome ore materials, you can add MgO to olivine. MgO converts the silica that's in the serpentine and the talc to phosphorite, to this material, to MgO SiO2. So it can eliminate some of the silicates. And MgO can combine with phthalate to form this magnesioferrite. We've mentioned this phase before, MgO Fe2O3, which melts at a higher temperature, 1713 degrees C. So MgO converts these two magnesium silicate, serpentine, and talc to a higher temperature phosphorite, and MgO can combine with the iron in phthalate to form a magnesioferrite and phosphorite. Now, under oxidizing conditions, FeO and phthalate oxidizes to Fe2O3, and then that basically liberates silica. So the phthalate can decompose under oxidizing conditions to Fe2O3 and SiO2. So you start out with olivine, which contains phosphorite, MgO, which is a dead burned MgO, and they're again crushed and sized and screened to the appropriate sizes to give the right particle packing. For a dense material, goes through mixing, a small amount of water, perhaps organic binders are added for dry pressing. It's dried and it's fired. The typical range here is 1400 to 1800 degrees C for the firing temperature. And the microstructure, if it's a conventional bonded material, and these are primarily conventional bonding, it's going to be phosphorite and small amounts of MgO and magnesiopherrite separated by a silicate phase. So you're kind of stuck with this microstructure, and the silicate phase is going to control the high temperature behavior as in all these, as typical for other materials that we've just talked about. So you're going to end up with phosphorite, MgO, and magnesiopherrite separated by a silicate glassy type phase. So the properties, the deformation under load is not very good for these materials because of the silicate phases that are present. They're going to melt and become less viscous at lower temperatures. So hot strength, creep resistance, not very good. However, they're excellent in slag resistance, especially when you have iron oxides are present, because they can tolerate iron oxides and not lower the melting point that much. Thermal shock resistance is poor because it's a high thermal expansion material. So just like a lot of other refractory materials, some of the properties are going to be a compromise. You can have a good property here, but then you have to be aware you might have a good slag resistance, but low hot strength and poor thermal shock resistance. This seems to be the way for a lot of the refractory materials. Some of the properties are outstanding and some aren't. I don't think you can find one refractory material with all the properties that we discussed the first couple of days in the excellent category as a function of temperature. You always have to consider how the properties vary and which properties are important for your application, because you're not going to maximize and have excellent properties across the board here. So here are 3 phosphorite refractories with different MgO contents, 55, 60, and 65%. Lower bulk densities around 140 pounds per cubic foot. These have a lot of porosity, around 30%. Cold crushing strength is relatively good because there's a lot of silicate phases present that are rigid at room temperature. So silicate glass gives rise to high room temperature strengths, whether it's cold crushing or 3-point bending. The RUL, which is the refractoriness under load test, we discussed that, where you heat it up at a constant temperature until the material deforms, basically fails. So you can see some of these temperatures, especially this one's not very high, 13, 16 degrees C. So that's where it completely deforms in this test. These other ones are not that much better. So these are the MgO contents, 55, 59, and 66%. SiO2 is primarily the balance, 33, 28, and 17. These have impurities, quite a bit of Fe2O3, about 7, 8, and 13%. And then your other impurities, Al2O3 and CaO. So that takes us through almost all of the basic refractories except spinel. It's almost 12:30. So I think I'll stop there. We'll finish up at 1 o'clock on the spinel materials. I think there's one test I put in there on hydration resistance because of the lime component in a lot of these materials. And then we have a shorter section after lunch on insulating refractories, the insulating refractory brick, IFBs, and then fiber-based materials. So we'll take a break here and then come back after lunch about spinel refractories. And that's the last basic refractory composition. And then we'll finish up today with insulating materials. And we mentioned spinel refractories, or we mentioned spinel phases in other refractories. So by itself, just like phosphorite, it is a viable refractory material. So the raw materials for spinel is MgAl2O3, a melting point of 2105 degrees C, which is about 28.5% MgO and 71.5% Al2O3. Spinel is a synthetic man-made material produced from alumina and magnesia. So there's two forms of man-made spinel. One is sintered and one is fused. The sintered material is calcined at a low temperature, formed into pellets or briquettes, then sintered at 1800 degrees C, relatively high temperature to densify it, then it's crushed and sized. The fused material is melted at 2200 degrees C, and then it recrystallizes upon cooling to form dense. This should be alumina MgO crystals or spinel crystals. So MgO plus Al2O3 forms MgAl2O4. So the sintered process for forming spinel, you start out with alumina and MgO. These are calcined at lower temperatures, so they're not densified. They're mixed together in a milling process. They're granulated, they're dried, and then they're sintered. These pellets are then crushed. You can remove iron at this stage and screened into the various sizes for the product. The fused spinel, same raw materials, alumina and magnesia. Now they're put in an electric arc furnace and melted. They're poured into ingots. When they're cooled, they're crushed. Iron can be removed again, and they're finally screened into the sizes for the various products. So the fused spinel is basically close to 0% porosity, whereas the sintered spinel has your typical 10, 20% porosity. The MgO Al2O3 phase diagrams, if it's spinel and it's stoichiometric, it's MgO Al2O3. It can be rich in MgO. So in that case, you're going to have periclase, which is MgO and the spinel phase, or it can be rich in alumina. And if it's that case, you'll have corundum, which is Al2O3, and then your spinel phase. So this is the part of the MgO Al2O3 phase diagram. So this is 100% MgO on the left and 70% Al2O3 on the right. And the right vertical axis is stoichiometric spinel. So we're just looking at the MgO rich side of spinel right now. So 100% MgO, 70% Al2O3, or actually a little more than 70% for spinel, and then temperature. So the lowest liquid forms at 1995 degrees C. So it's a high temperature material. 2105 is the melting point for spinel, over 2800 for periclase or MgO. So it's a very refractory material. And if we look at the other side of the phase diagram, from spinel to 100% alumina, again, it's temperature versus the composition. The first liquid phase forms up here about 1900 degrees C. So here's your spinel solid solution. Here's your spinel plus alumina. Here's your spinel solid solution. And here's your spinel plus MgO. So this is an MgO-rich spinel. This is an alumina-rich spinel. And this line is the stoichiometric spinel. So to make a spinel refractory, you start out with spinel, whether it's fused, man-made, or some combination. Again, you're going through the crushing, screening, and mixing operations. A small amount of moisture is added for dry pressing. It's dried and then firing in this temperature range, 1400 to 1800 degrees C. So this material has fairly good thermal shock resistance, has average or moderate slag resistance, and has very good deformation under load, good hot strength, and creep resistance. So this microstructure is basically polycrystalline spinel. Here's two versions, 85% MgO and 90% MgO. So these are periclase-rich spinels. You can see the alumina content is quite high, 85 and 90, and then the MgO content is quite high, 85 and 90, and the alumina content is primarily the balance. So these are both spinel plus MgO. So spinel and periclase are the two phases, polycrystalline materials. Density is about 180 to 185. Porosities around 17%. Cold MOR over 1,000 in both cases, and cold crushing over 5,000 in both cases, relatively good. And this one has very good hot strength at 2400 at 2300 degrees F. And this one is still reasonable. It's not that high at 670 PSI at 2500 degrees F. So those are the two examples of a magnesia-rich spinel. And there's only one test, one ASTM test in this section, and that's the hydration resistance. And I mentioned that when lime's present, the material can hydrate rather quickly, and even MgO can hydrate at a much slower rate. So this hydration resistance test determines the relative resistance of basic bricks to hydration, and it's an accelerated test. So the samples are exposed to steam under pressure in an autoclave to accelerate the hydration. The test can be used to predict whether or not basic bricks or other shapes will hydrate in storage or in service. And I mentioned that dolomite will hydrate rather quickly in storage unless it's protected. It still has a relatively short shelf life. You can also use this test to estimate the relative potential for hydration. So 1-inch cubes are used in this test. They're cut from 5 separate samples, 5 bricks or refractory shapes, and they're cut from the interior portion of these pieces. For the equipment, you need an autoclave that can at least operate to 80 PSI and 162 degrees C. That's the operating parameters for this test. The dry samples are placed in porcelain crucibles. In case they disintegrate, the crucible will retain the material, and then they're loaded into the autoclave, and it's held for 5 hours at 162 degrees C and 80 PSI. And when the test is done, it's another visual rating, just as for CO disintegration and alkali vapor attack. 1 is unaffected. 2, if you see surface hydration. A Powder forming on the surface would be a rating of 2. 3 if it's actually cracked or crumbling, and 4 if it's completely disintegrated. So you repeat this test, the same procedure on the same 5 samples for successive 5-hour periods up to 30 hours. So you can repeat the test up to 6 times or until all the samples have a rating of 4. So you repeat the whole procedure 6 times and keep monitoring the sample. And if it disintegrates, you stop the test. So that's a hydration test for these basic refractories. The last topic today is insulating refractories, and there's 2 types here. The insulating fire brick, that's IFB, insulating fire brick, and insulating fiber. RCF is refractory ceramic fiber, and AES is alkaline earth silicate fibers. So we'll do the insulating fire brick first, and we'll discuss the background, how they're processed, and their properties and applications. So the insulating fire bricks were developed in the 1930s for low thermal conductivity. So to get low thermal conductivity, fine pores were introduced into the structure. The conductivity of air is very low, especially when compared to a refractory material. So for example, the thermal conductivity of a zircon refractory at room temperature is 1,600 times greater than that of air. So if you introduce a lot of fine pores into the microstructure, you're going to decrease the thermal conductivity. And when we looked at the equations under properties for radiation, photon conductivity, that equation had the pore size in it, and the smaller the pore size, the lower the conductivity. So they're lightweight. The porosity is rather high, 50 to 85%. That gives a really low bulk density, 0.4 to 1.6 grams per cubic centimeter. You use IFBs because you can conserve energy, and you can do this 2 ways. You can have a reduction in both the lost and stored heat. So you have shorter heat up and cool down times because your furnace wall is made of an IFB, so that they take up less heat. You lose heat, you lose less heat through the wall of the furnace because it's an insulation material, and it takes less heat to heat up the furnace. So there's trade-offs for using these insulating materials. The high porosity level means the structural strength is low, so cold crushing strength or bending strength is very low. High porosity, well, we determine that the higher the porosity, the more the material will corrode. So you have decreased corrosion resistance with the high porosity, and actually you would not use this material in contact with a slag or a glass because they would not last very long because of the high porosity. It's relatively weak, and with all the porosity, it has very poor abrasion resistance. So you've weakened it, and you decrease the corrosion resistance, but you increase the thermal resistance at the insulating behavior. So how are these made? You introduce porosity by adding a material that will burn off during the firing process. So you add a combustible material to a refractory slip. So these are slip casts, they're not pressed. So it's a fluid liquid solution for slip casting. The combustible materials are usually sawdust, but they can be a polymer like a polystyrene bead, walnut shells, they can be ground coke or anthracite. Some of these materials are going to have some ash left over when they're combusted, so they will add some impurities to the IFBs. So slip casting is used to maintain the high porosity level during the forming process. You don't want to apply pressure and densify it like in a pressing operation. The slip cast shape is, or if you cast a brick shape, it is dried, then it's fired. And when that happens, you burn out the combustibles, you leave voids where the combustibles burn out. And now you have a highly porous shape or brick shape. But you usually can't make these to any type of dimension. You can't hold a tolerance. So they're usually cast oversized into large blocks, and then they're cut and machined to the final brick shape. So then they have excellent dimensional control in the forming process. So because of a large amount of shrinkage that may be taking place, and you can't maintain dimensional stability during the firing process, these oversized shapes are cast and cut after the firing process, and they're relatively soft and easy to cut. So you start out with whatever refractory raw materials you're going to use. It could be a clay, it could be a kaolin clay, it could be alumina. You add a combustion type material, whether it's sawdust, walnut shells, or some type of polymer. You form a slip with water and electrolytes. The electrolytes create a charge on the particles and they stay in suspension. It's slip cast in some type of porous plaster Paris mold, which removes the water. It's dried and then fired over this temperature range, depending on its chemistry. If it's high alumina, it would be fired at 1700 C. If it's a lower grade IFB, it would be fired at 1000, 1100 degrees C. The combustible burns out during the firing process. Now you have a large oversized shape. You cut it and machine it to whatever size you want. Usually it's a 9-inch straight. So you can also introduce porosity by entraining air into the slip by using some type of foaming agent. You can also add porosity by the addition of other ingredients that react to evolve a gas over a period of time during the forming process. So introducing porosity by methods, either one of these above, by entraining air with a foaming agent or evolving a glass, can have an advantage compared to the addition of combustibles. Some of these combustibles are going to have an ash content. So there's a percent ash, which is high in silica and alumina and alkali. So the ash will reduce the refractoriness of the IFB or lower its use temperature, depending on how much ash is present. And you're using a great deal of combustibles because you're trying to achieve 50 to, let's say, 80% porosity. So IFBs are generally ranked by the use temperature, and these are the common ones: 2300 F, 26, 28, and 3000 F. So a 2300 degree F IFB would certainly be useful to like 50 degrees lower than this temperature, or 2250 degrees F. This one would be useful to about 2950 degrees F. So as you go up in use temperature, you're going up in alumina content and you're going up in density. As you go up in density, you also go up in strength, whether it's compressive strength or bending strength. They both tend to increase with increasing alumina content and density. And these are the thermal conductivity values in the BTU units at 400, 750, and 1100 degrees F. You can see that they generally increase or stay about the same. There's no large drop off. There's not a lot of photon or radiation conductivity present at these temperatures yet, so it's basically fairly constant, but they're relatively low. These are a little higher than 1. These are about 3. compared to other materials like alumina and MgO, which are well over 100. So they're very low conductivity. Here's the alumina contents increasing with the use temperature from 51 to 73%, and the silica contents decreasing with the higher temperature materials from about 45 to 25%. Some of the impurities, again, are typical for refractory materials: Fe2O3, TiO2, and the alkali, sodium and potassium alkali. So these are the common IFB materials. You can also have some based on fire clay. And these are kind of randomly organized in this table. So there's different densities, different porosity levels, and strength levels tend to follow the porosity levels. Higher strength tends to go with lower porosity. The thermal conductivity is in this range 1 to 2, and the units based on BTUs. And this is a reheat shrinkage at 2350 degrees F. And these are also quite low, less than 1%. And these are the alumina contents, about 40%, the silica contents, about 50%, and then one of the impurities that are present. Not all the impurities are obviously listed here. So these are from actual data sheets. So the impurity levels are probably affecting these properties up here, like the cold crushing strength. So there's certainly a glassy phase present in these materials based on the impurities. You can also have higher alumina content IFBs from about 32 to 68 weight percent. 32 to 68 bulk density in pounds per cubic foot. These porosities are all pretty high, 65 to 83%. The cold crushing strengths depend on the exact chemistry and how they're fired. And you can see again, these are at 500 degrees F, relatively low thermal conductivities. And the reheats are at a whole range of temperatures here, 2750 up to 3000 degrees F. And basically a reheat less than 1% is excellent, less than 2% is still good. So these are all less than 1%. These are the corresponding alumina contents, silica contents, and one impurity, Fe2O3. So you can see that when you add some of these up, like 64 and 32 is only 96%, and you add that, it's 96.7. So the data sheets here are not complete with the other impurities. And the last one, I guess, here to show you is that you can have a material based on alumina, basically 100% alumina, or you can have a silica material, almost, well, this is about 94%. Not shown is probably the CaO, which is the mineralizer, probably 3% there. Cordierite, which is that magnesium aluminum silicate. It's a low temperature material. So it's about 53% alumina, 32% silica, and 12% MgO. And you can have a spinel also. This is an alumina-rich spinel at 67% alumina and 26% MgO. The porosity levels just depend on how they're processed, but roughly 50 to 70%. The cold crushing strength is dependent on the chemistry and the firing temperature. The high alumina is quite high in cold crushing strength. So as you go up in alumina content, you're going to have a higher thermal conductivity. This is 6.3%, 6.3 in the BTU units at 500 degrees F. and these are a little bit lower. So again, the reheats, this one's quite high temperature, 3250. So this must have a use temperature of about 3300 degrees F. This use temperature would be about 2800 degrees F, so it's reheated at 50 degrees lower. This would have a use temperature at 2600, and so would this one. So the reheat values are quite low, and they're quite good. So I just wanted to show you that you can have basically a pure alumina IFB, a pure silica, and different compositions like cordierite or spinel. And if you look at thermal conductivity versus temperature for all the different types of refractories, MgO is quite high. And this is, again, the BTU units. This MgO starts out about 80 and goes down to 40. But the insulating fire bricks are all in the 1 to 2, maybe 3 range. So they're much lower than MgO, Al2O3, zircon, the fire clay materials, and the semi-silica material. So they're quite low. There's an insulating alumina, which would be a high alumina, which is a little higher. And this is a silica insulation. It must be lower in porosity. It's a little bit higher, but the IFBs are generally much lower than all the other refractory materials. So IFBs they can be used as an inner lining, hot face, or as the outer lining backup. So if they're used as an inner lining, they're not suitable for contact with a molten metal, a slag, or glass because of the high porosity. So they're not also suitable for areas exposed to corrosion and abrasive conditions because they're very weak and high porosity. And the furnace atmosphere may have an effect. If it's highly reducing, you may have to have a low FeO content because it may reduce or oxidize materials in the IFB. And you have to be aware of mechanical shock or vibration because these are relatively weak materials. You have energy savings when you're using an IFB on the hot face of a furnace. It reduces the heat loss, and there's less energy stored in the lining when you heat and cool it. So an example of an IFB, how it impacts heat and heat flux. If we have a shuttle kiln, which is a periodic furnace where you put a load in the furnace, you heat it up, you cool it down, and you empty the load and you start again. So this is an example of a shuttle kiln operated at 1,000 degrees C over a 22-hour cycle. You have a 9-inch straight dense fire brick or a 9-inch dense fire brick lining. So that's the wall thickness. Can be made up of 9-inch straights, and 9 inches of insulating refractory again can be made up with 9-inch straights. So heating and sintering the wear. So whatever you had loaded in the furnace, just to heat it up, sinter it, and densify it, would be the same in both cases, about 20 times 10 to the 6 kilojoules. The loss of the stack, the heat loss will be the same, again, about 20 times 10 to the 6 kilojoules for each one. But now, lost in heating the refractory lining, since this is a dense lining, this one takes 27.6 kilojoules times 10 to the 6 kilojoules, and this is 1.32 times 10 to the 6. So much less heat required to heat up the lining. Loss through the walls and the heat up, the loss here is 8.5 times 10 to the 6, and this is 0.48 times 10 to the 6. Loss through the walls at steady state, 8.5 when that's on the whole temperature, and this is 0.65 both times 10 to the 6. So the total heat consumed per cycle, this is 84.6 times 10 to the 6 kilojoules, and this is about half, 42.45 times 10 to the 6 kilojoules. So the energy efficiency here is 23.5%. The energy percentage that went into producing whatever is in the furnace divided by the total heat required, and this one is almost twice, actually is twice, 47%. So it's much more efficient to use an IFB instead of a dense fire brick. You save in heating up the furnace, wall, loss through the walls during heat up and the whole time. So inner lining, hot face selection criteria. You have to be aware of the service temperature limit. That's just abbreviated STL. Considering IFB permanent linear change, I will go over that test shortly, but it's a 24-hour hold at temperature. So it's a 24-hour reheat test. If the reheat test is less than 2%, you can use the material at 200 to 300 degrees C below the reheat temperature. If it's less than 0.5%, you can use it 1 to 200 degrees below the reheat temperature. Those limits give you the temperature, the use temperature where no more shrinkage should take place. Consider a RUL type test, subsidence under load at whatever temperature the material is rated at. If it's less than 2%, again, you can use it 200 to 300 degrees C below the low temperature. Less than 0.5%, you can use it 100 to 200 degrees C below the low temperature. So these numbers here, these different percentages give you an idea of what temperature you should be able to use the IFBs at. For the outer lining, so you can use the IFBs as an inner lining as long as it's a furnace that is not containing a slag or a glass or corrosive atmosphere or mechanical issues. You can also use it as a backup in any of the other situations. So when an IFB is used as a backup to some type of working refractory lining, you have to consider what happens at the interface. What is the temperature between the IFB and the working lining? These use limits still apply. So if the composition of the IFB is different from the inner lining refractory, you have to be careful in selecting appropriate chemistry of the IFB so that it won't react with the inner lining. And you have to worry about the furnace atmosphere. Even though they're backup, they're still going to be affected by the atmosphere and can be subjected to a reducing or oxidizing condition. So a duplex lining, which would be using the IFB as a backup under steady state conditions where the furnace temperature is held constant and the heat flow through the wall of the furnace is steady state. So in some cases, the heat loss is necessary for the protection of the integrity of the hot face lining. So we talked about corrosion and the freeze plane. You have to be careful when you put a backup lining where you shift that freeze plane. You can slip it deeper into the material. So you change the thermal gradient in the working lining when you put a backup lining, and you can move that freeze plane into the working lining at a deeper distance and enhance the corrosion resistance. So if we look at a duplex lining where TH is the hot face, TI is the interface, and TO is the outside temperature. So we have a hot face temperature, an interface temperature, and an outside temperature. So it would look something like this. We have a hot face and a cold face. This is your inner refractory lining or working lining that could be in contact with a slag or a metal. This is an outer insulating lining, the backup lining, the hot face temperature, the interface temperature, and the outside furnace temperature. So the insulating refractory backup material will reduce the heat flux and increase TI. So by adding this material, instead of having a cold face here for the hot face, you now have a higher temperature TI. So when this happens, the average temperature of the inner lining increases, and it could decrease the corrosion resistance. So you have a less steep thermal gradient from the hot face to this interface. So it's a more shallow thermal gradient. The freeze plane will move in deeper into the hot face and could enhance the corrosion resistance. So you're saving energy by putting a backup lining, an insulating lining, but you could enhance the corrosion resistance depending on what the operation is. So those are some things to be aware of when you're using an IFB for either an inner lining or a backup lining. There's we've been talking about a reheat change. Well, C210, this test, is the reheat change for an IFB. So it measures the permanent, linear, and also volume change of an IFB when heated under a prescribed condition. And there are heating schedules for each different class of insulating firebrick. The importance of this test, well, it determines the thermal stability by reheat measurement over a 24-hour test period. And we gave some percentages, a 0.5% or 2%, which were the safety limits for using an IFB. You're testing a full-size brick, which is a cross-section of 4.5 by 2.5 inches or 4.5 by 3 inches, and the length is about 9 inches. You need a high temperature furnace capable of going to 3250 degrees F. It has to maintain the heating schedules according to the ASTM standard, and it's calling for an oxidizing atmosphere. So in this test, you measure the length, the width, and the thickness of each sample at 3 different locations. So you measure 3 lengths, 3 widths, and 3 thicknesses. Then you have to place the sample in the furnace so it rests on the 9 by 2.5 or 9 by 3 inch face. And you place that on a supporting brick of the same composition. You could put a refractory grid in between. So you don't want to restrict the shrinkage. If you place it on the furnace floor of a material that's not shrinking, there'll be some friction and that side of the brick will shrink less than the top. So you place it on a refractory brick of the exact same composition that shrinks the same. So there's no interference with the length change. You pick the heating schedule for the composition. And then after the test, you measure the length, width, and thickness at the same locations. So this is what a 9-inch straight would look like with the measurement locations marked. So the length is 9 inches in that direction. So you're measuring the center and a 1/2 inch in from each edge. The width is 2.5 or 3 inches, and you're measuring in the center, and again, a 1/2 inch in from either edge. And then this thickness here is 4.5. So you're measuring in the center, and again, 1/2 inch in. So you have 9 measurements to get an accurate linear change and a volume change. So these are the heating schedules for the different kinds of IFBs. This is the elapsed time from the start of heating to you reach the hold time, and the hold time is 24 hours. So we mentioned different groups. I think we did a 23, a 26, a 28, and a 30. So there's also a 16 to 20, a 32, and a 33. So the higher the number, the higher the use temperature. And all the tests are done 50 degrees F lower than these groups. So it's, group 16 is really a 1600 degrees F fire break, and you reheat it at 1550 F. Group 33 has a much higher use temperature. So it's supposedly a 3300 F material reheated at 3250. So these are the heating rates. Obviously, the higher the group number, the higher the temperature, and the hold times are all 24 hours. We've seen this equation a lot. The percent linear change is the final length minus the initial length divided by the average length times 100. So you calculate the percent linear change. You also calculate the percent volume change. So that's the final volume minus the initial volume divided by the initial volume. And in both cases here, you're multiplying by 100 to get a percent. A typical reheat report would look something like this. This one was a 2800 degree F reheat for 24 hours. So the material was initially dried at 230 F, and you measure 3 lengths, 3 breadths, and 3 depths, and the weight. So the dried bulk density in this case was about 58 pounds per cubic foot for each one of these. Then you fire it, and you measure the 3 lengths, breadths, and depths again, and reweigh it. Now the bulk density is a little bit higher, 60 or 61 pounds per cubic foot. So it did shrink, and it's a bit denser. So these are the values for the 3 lengths, 3 breadths, and 3 depths. You can see that they're slightly negative, 1 to maybe 3%. So there's some shrinkage. There was a little weight loss. And then the volume losses in these cases were about 4 to 5%. So really you report the average volume change. So there was a decrease in volume. And so this might be borderline using at that temperature because the length changes were on the order of 1 to 2%. So that's a reheat test for characterizing the use limit for these IFBs. The last section here is fiber insulation. We'll do the same thing as we did for IFBs, the background, how they're processed, and the properties. RCF is a refractory ceramic fiber. AES is an alkaline earth silicate fiber. So these fibers were developed in the 1940s, the RCF fibers. They became commercial products in the 1960s. And they're generally aluminosilicate fibers. Some of these fibers also have zirconia in them, but they're basically aluminosilicate fibers. The AES fibers are alkaline earth silicate fibers. They were developed in the 1980s. They were commercially available in the 1990s. And they have low bio persistence. And that means if you get fibers in your lungs when you're working with it, they will dissolve in a reasonable amount of time and not be a health hazard. So these fibers were developed to eliminate health issues associated with more stable fibers that are biopersistent. So the raw materials, whatever you're using for whatever composition, are melted in an electric arc furnace. And there's 2 processes for making fibers. There's a blowing process where a fine stream of molten material is tapped from the furnace, and then it's fiberized by a stream of high pressure air or high pressure steam. So this molten stream that's tapped from the furnace is subjected to a high air or steam pressure, or there's a spinning process which utilizes a high-speed rotating disc or rotor of some type. So the stream of molten material flows onto the disc is spinning, and it generates the fibers. So two common processes for making fibers. When you make fibers, you also produce shot along with the fiber. And shot is an unfiberized spherical particle, so you generate these small spheres or shot. And they can be as high as 40%. Hopefully they're much lower than 10%, but they can be a high percentage of the weight of a fiber type material. So you have to be aware of the shot content, and I'll describe a test for measuring that later. So you have your refractory raw materials, whatever you're making. It could be clay, kaolin, alumina, calcia, zirconia. So you need to pick the raw materials for the appropriate composition, melted in an electric arc furnace. If it's a blow forming process, you use high pressure air or stream. If it's a spinning process, you use a high-speed rotating disc or rotor of some type. And you end up with ceramic fiber plus shot in both cases. So you're making a fiber material, whether it's a blanket or a board or loose fiber. The thermal conductivity is the property you're looking at for lowering the thermal conductivity, making it an insulating material. So the conductivity of the fibers is controlled by the diameter, the shot content, and the bulk density. So as you decrease the fiber diameter, you decrease the solid state or phonon conductivity. You have less cross section, so you're simply decreasing the solid state thermal conductivity. If you decrease the shot content, you decrease the thermal conductivity. Obviously, the shot is not a fiber. It's going to be an area of high solid state thermal conductivity. And if you increase the bulk density, you decrease the thermal conductivity, which is a little bit different than an IFB, because if you increase the bulk density of a fiber blanket or a fiber board, you're really making the pores smaller and decreasing the radiation component or the photon conductivity. So decreasing fiber diameter, decreasing shot content, increasing bulk density, all decrease the thermal conductivity. So the thermal conductivity of the ceramic fibers is dominated by radiation at the higher surface temperatures where radiation is important. So the fiber area, surface area actually controls the thermal conductivity. So the heat resistance of the fiber depends greatly on the shrinkage that's going to occur at the surface temperature. The aluminosilicate fibers have an alumina content between 40 and 60 weight%. When you form this fiber, you have a stream of molten glass, basically an amorphous material, and you quench it by either spinning it or blowing it with an airstream. You're quenching it and you're freezing in this amorphous structure. So it's a glassy or amorphous fiber. And then when you heat it up during use, you're going to crystallize it. And in this particular composition, you're going to form mullite when you start reaching temperatures around 1,000 degrees C. And then when you hit 1,300 degrees C, you're going to start forming crystolite. So when you start crystallizing these materials, going to a denser crystalline phase compared to the amorphous phase, you're going to have a volume shrinkage. So these are some alumina silica fibers, and these are the alumina contents from about 30 to looks like 60 weight percent. And these are the surface use temperatures. The higher the use temperature, the higher the alumina content. The specific gravity is going to also be a function of the alumina content. These fibers are relatively small. They're about 2 to 3 microns in diameter. So very small diameter fibers. These are the alumina contents that have to correspond to what they're rated for. The balance is silica, except in a few cases here, in this one and this one, some Cr2O3 has been added to enhance the properties. And this one has ZrO2. So this one has quite a bit, about 15% in each case. So whatever application, maybe there's a gas phase in this one and you wanted a little more corrosion resistance, you might have added ZrO2. Same thing with this chrome addition. So this is an SEM photograph of the Aspun fibers. You can see they're random in length and diameter. And you see these large spheres here. Here's one, here's another one, here's one, and some of them are a little bit odd shaped. Well, that's the shot content, the unfiberized material. And if you look at a higher magnification, this is about a 50% alumina, 50% silica fiber. And these are roughly 2 to 3 microns in diameter. And you can see the diameter is variable and the length is also variable. You can make mullite alumina fibers, so it's a higher alumina content. So mullite is typically between 72 and 80% alumina, and then alumina fibers are going to be much higher, 94 to 97%. And you can have zirconia fibers, and they can be stabilized. You can use calcia, or in this case, I've listed yttria, Y2O3. Here's some of the higher alumina content fibers. Their surface temperatures are higher, maybe 29 to 3100 degrees F. These are the specific gravities or densities in grams per centimeter cubed. They're all around 3 to 4. These fiber diameters are around 2 to 4 microns in diameter. These are the alumina contents that have to correspond to the specifications. The balance being silica. So the crystalline phases that develop when you put this in service, well, they're all going to develop mullite, the alumina silica material. And then these that have much higher alumina contents, greater than 70%, are also going to have excess alumina, so they're going to have corundum present. So these are the phases that are going to crystallize in this fiber system. If you produce a fiber based on zirconia, these are 290% and 100% materials. These surface temperatures are much higher, 4,700 degrees F, because they're a high temperature material. They're denser, so the specific gravity is closer to 6. And these fibers are about 3 to 6 microns in diameter. So zirconia ZrO2, in this case, is about 91, in this case, about 92, and in the 100% material, it's about 99. Zirconia always has associated with it some hafnium oxide. So there's a small amount, perhaps a trace, maybe even a little bit higher than a trace of HFO2 in this raw material. A stabilizer used here is Y2O3 yttria oxide, about 8% here, about 7. This one has no stabilizer. We'll talk about zirconia when we talk about special refractories in detail and its phase transformations. But without a stabilizer, it's in the monoclinic form. With the stabilizer, it's in the cubic form. When you put it in the cubic form, you eliminate phase transitions, similar to the phase transitions that were in silica, like the alpha beta quartz transition. So these have no transformations. There's also a third phase tetragonal. So this one is not stabilized. These two are. The other type of fibers are the alkaline earth silicate fibers, and these are biodegradable. The silica content ranges from 60 to 80 weight percent, and the balance is calcium, magnesia, CaO, and MgO. Again, low biopersistence, so they're safer to use. But these compositions are only useful to about 1300 degrees C. Here are two examples, a 60% silica and a 75% silica. These are the surface temperatures in degrees F, 2200 and 2400. The specific gravities are about 2.7 grams per cubic centimeter, 3 to 5 micron diameter fibers. The silica content corresponds to these two levels. Now the balance is CaO and MgO. So those are alkaline earth silicate fibers. Again, safer fibers, but lower use temperatures. So zirconia, alumina, mullite fibers are all formed with a precursor method. So zirconia, I showed the use temperature was rather high. So is alumina. It's a high temperature material, and mullite is even a high temperature material. So they're not formed by melting and a blowing or spinning process. They're formed by using a precursor, because melting these materials is not easy. It requires high temperatures. So the precursor is a solution, and you're forming these at basically room temperature. So it's a solution that, when heated, converts to aluminum, mullite, and zirconia. So the solution can be fiberized or blown in a temperature, humidity controlled atmosphere. So it's basically room temperature or low temperature. You control the humidity. And in some cases, the humidity, the water in the atmosphere causes the polymerization to start. But the solution is fiberized or blown at a relatively low temperature in a controlled atmosphere. And then the final fiber is produced by drying and going through the firing process. So you're forming the fiber at a low temperature because these materials are just too high temperature to deal with and melt and form fibers in the typical manner. So these ceramic fibers can be used to form a number of products. They can be put in blanket form. There's usually no binder in a blanket. The fibers are just interwoven to retain a shape. It's a soft, flexible material. That's why it's called a fiber blanket. They're usually a 1/2 inch to 2 inches thick, and they are shipped in a roll form. It can be a block or a module made up from a blanket. So you can fold a blanket and cut it to the desired size, and you can use it as a furnace lining. That folded blanket can be attached to a furnace wall with a metal blanket and to form the lining for that furnace. You can make it into a fiber board with inorganic binders, and now you have a rigid, self-supporting material, And that also can be used as a furnace lining. So two forms are common, the blanket form and the board form. You can form other shapes by adding inorganic binders to the ceramic fiber. Then you can make special shapes by using a vacuum forming process. You have electric heating elements. You can embed them in a fiber rigid material. So that incorporates an electric heating element for a furnace wall. So electric heating elements can be included in the shape to produce a low mass furnace lining with embedded heating elements. You can make the fibers into textiles, rope, bulk. You can use them loose fibers in the bulk, felt, or wet felt, or you can add them to other materials like gunning mixes for fiber reinforcement. So this is a fiber blanket that's been folded. And you can see how it's folded back and forth in this manner. There's a strap around it to hold it in one piece. So this would form a wall and a furnace. This would be the inside of the wall, and the other side would be the back side. There'd be some kind of metal bracket put on this that retains the shape and holds it in place on the wall. And these bands would burn out. So that's a fiber blanket that's formed into a module. So for some of the properties, these are 1800 and 2200 degree F use temperatures, and bulk densities in pounds per cubic foot are usually in increments of 2. So there's a 4, 6, 8, 10. So they try to hit these different bulk densities, 4, 6, 8, and 10, etc. These are the reheat shrinkages. These were less than 2% at 1800 degrees F. These were about 2.3 at 2150 degrees F. These are the thermal conductivities from 600 to 1600 degrees F in BTU units. And you can see these are really fairly low numbers from about 1/2 up to 2. And if you look at these, the denser material, same composition. You can see the compositions are identical. They're just formed to 2 different densities, a 6 and an 8 and a 4 and a 10. If you look at the 8 compared to the 6, it's denser, but the conductivity is lower at all temperatures. And the same here, it's a denser material and a lower conductivity. And that's because we're creating smaller pore diameters or effective pores between the fibers that are in these modules. Here's a couple more materials, 2 2450 degree F materials and a 2800 F material. So these have alumina contents around 35. This is 72. The balance here is about 48% silica and about 16% ZrO2. So this is a composition designed to be a mullite. This is 6 and this is 8. This density wasn't given. These shrink about 2.8%. This is about 1%. And again, same composition going to a denser material. If you look at these two ranges of thermal conductivity, the one on the right is a little bit lower than the one on the left, even though it's denser. And then a couple more at 2200 degrees F and 2400 degrees F. They're the same density, but they're different materials. These are this is the alkaline earth silicate, AES material. It's silica, lime, and MgO. And this is one without MgO, just silica and lime. So different compositions. Reheat shrinkage is less than 2%. This is at 1800 and 2300. And these are the thermal conductivities at as a function of temperature. So about 0.4 to about 3, so still relatively low. This is what a fiber board looks like. It's a rigid board. So this is fibers that are pressed with an inorganic binder. This one says 3,000, so it's a rated for that temperature, 3,000 degrees F. These are more complex shapes by vacuum forming. So this could be maybe a furnace lining with the elements embedded in it. And these are forming some type of cylinder. So you can vacuum form complex shapes. And finally, for the insulating fiber board, these are 3 different use temperatures, 21 to 2750 degrees F, 3 different bulk densities. Reheat values are basically 1 to, this one's pretty high, 3.5. And then their thermal conductivities that correspond to the different bulk densities. Again, they're fairly low thermal conductivities, different compositions. There's an alumina range from about 35 to 60, silica range from about 40 to 55, and this one contains zirconia. So those are examples of the fiber blanket materials and then the fiber board materials. And then the last thing today is to go over a few of these tests to characterize the insulating fiber materials. So I mentioned shot content. Well, there's a test embedded in C892 that measures the fibrous shot content. So to do this, you dry sieve analysis, a method by dry sieve analysis that can distinguish between the fiberized and the non-fiberized or shot portions. And they define shot as a material that cannot be brushed or mechanically shaken through a 70 mesh sieve. That's 212 microns. So the fiber diameter, if you recall, is generally between 2 and let's say 6 microns. So they're assuming all the fibers are going to go through a 70 mesh screen, and all the shot will not go through the 70 mesh. So that's anything bigger than 212 microns. It's important because you need a measure of the shot content because that does not contribute to the insulating value of the fiber insulation. And it's basically a determination of quality of the fiber insulation. Obviously, a lower shot content is a higher quality, a better insulating material. You're measuring samples on the order of 10 grams. So you select 3 samples of the fibrous material in 10-gram lots. You need a furnace, a low temperature furnace capable of going to 2300 degrees F. And you have 3 standard sieves, 30, 50, and 70 mesh, 70 being the finest and 30 being the coarsest, and a balance to weigh the material. So what you do is you heat treat the sample at 2300 for 5 hours. That crystallizes all the fibers. They become more brittle. So a crystallized fiber is more brittle, so they can be broken up more easily. So you manually, with a brush or a rubber stopper, basically just press on the material and force it through these sieves, 30 and a 50. And then you shake it in a mechanical shaker in a stack of these 3 sieves, 30, 50, and 70 for 30 minutes. And then you weigh the material retained on each sieve. And that will be the shot content. So the percent non-fibrous material, WC, percent non-fibrous material retained on a sieve, is just WP weight of material on that sieve divided by WT, total weight after heat treatment. To get percent, you just multiply by 100. So you add the material retained on each sieve, the 30, 50, and the 70 sieves, and you get the total shot content. So very simple report here. This one was actually a fiber blanket fired at 2000 F. And this weight of this one sample is a little more than 10 grams. And to blow these reports up, I usually cut off the other test results. But here's your US sieve numbers, 30, 50, and 70. Here's the weight retained. Here's the incremental weight. And here's the cumulative weight. So this has a shot content of 5.37 weight percent. So that's pretty low. So that's the test to measure shot content. I mentioned that reheat shrinkage was important because you don't want your lining to shrink and open up cracks. And that would cause issues with the shell of the furnace if it's a metal shell. And also you would not have the same insulating capability. So you have to measure the permanent linear change of the insulating material when exposed to some high temperature. They call it a soaking heat because you hold it for 24 hours. So you define the thermal stability by reheating for 24 hours at a particular test temperature. If you have excessive shrinkage, that indicates that the use temperature has been exceeded. You obviously aren't going to use a material that shrinks at your use temperature. For either a fiber blanket or a fiber board, you cut a rectangular prism 6 inches long, 2.5 inches wide, and the thickness is 1.5. Now, if you only have an inch thick fiber board or blanket, you use that original thickness, so it could be less than 1.5 inches. You can use a gas or electric furnace in this test method. You have to control the temperature fairly accurately to within 1% of whatever test temperature you're using. You have to have some kind of apparatus to measure the fiber blanket and fiber boards, especially the fiber blanket, which is kind of a soft material. So you don't want to crush these materials when you're measuring them. So there are some apparatus that you can either build and avoid crushing the samples, or simply you can use calipers with metal plates. So you measure, you put the plates on the edges of or faces, opposite faces of in whatever direction you're making the measurement. You put a thin metal plate and you measure that in total thickness and you subtract the metal plates off. So it can be that simple. And you need a balance to weigh the materials. So you dry the samples at 250 degrees F, weigh them, and you measure the length at one location, the width at 2 locations, and the thickness at 2 locations. You put the sample in the furnace so that it rests on the 6 by 1.5 inch face, or if it's less than 1.5, whatever dimension that face is. And you rest it on 3 cylindrical bars. So 3 high temperature ceramic bars of some composition. And they have to be bigger than 1/2 inch in diameter. So your samples are sitting vertically in the furnace on these bars. You heat the samples not to exceed 300 F per hour, and you hold them for 24 hours at a soaking temperature. So you measure the length, width, and thickness of each sample after reheating at the same location, 1 length, 2 widths, and 2 thicknesses, and reweigh them. And you get the percent linear change S equals L1 minus L2 over L1. S is the percent linear change. L2 is the average final length, whether it's a length, width, or thickness. L1 is the average original length, again, and whether it's a length, width, or thickness. You get the percent weight change. C is the percent weight change. W1 is the original weight. W2 is the final weight. The difference is divided by the original weight times 100 again for percentage. And the report would look something like this. This is the C356, reheat shrinkage on thermal insulation. This sample was dried at 110 degrees C and then reheated at 1100 degrees C and held for 24 hours. 4 samples are used for the average, and you can see there were 3 lengths, 3 widths, and 3 depths, and the weight measurement. So the bulk density on these in pounds per cubic foot were between 7 and 8 pounds per cubic foot prior to reheating. So it was fired at 1100 for 24 hours, and you remeasure these lengths and the weight, and you calculate a new bulk density. So they're slightly denser, so there's been some shrinkage. And then you can do the change in length 1, 2, and 3, or breadth 1, 2, and 3, and depth 1, 2, and 3, and the weight change. So you get a volume percent decrease. So volume 1 was in this range, 0.2 to maybe minus 3%. Volume 2 is about 1 or 0.7 to 4. Volume 3 is in the same range, about 0.4 to a little higher, maybe 5. So those are the shrinkages of the 3 volumes, the way you calculated them from the 3 sets of measurements. And the average volume is what you're interested in. Minus 2, minus 0.4, minus 4.3, and minus 2.2. So they're quite variable here for this particular material. So that's the reheat shrinkage, and that's important for determining the use temperature. These are higher. If you average the average, it's probably a little higher than 2, so that's probably a little bit beyond the use temperature. So that was a test for shot content and reheat shrinkage for the fiber boards or fiber blankets. So we finished up the basic refractories, and then we did insulating fire bricks and insulating fibers. Are there any questions on any of that? Try to cover quite a bit of material here. So tomorrow we'll do monolithic refractories, which are castables and other types of mix that are formed in situ and then fired during use. So there's no processing where you form a brick or a shape. It's actually cast or shaped into a furnace lining. And then we'll also do the non-oxide refractories, which are carbon, silicon carbide, and silicon nitride. So we'll do that tomorrow. If you have any questions in the meantime, some of you have emailed me a few questions. You can certainly email me and or give me a call. So it's getting close to almost 2:30, so we'll stop there, and I'll be here tomorrow at 11 o'clock. Thank you for your time and attention. Bye.
Thank you. Bye.
You're welcome.
Bye, thank you.